Hello everyone, welcome to COMP359, Design and Analysis of Algorithms. In this video, I'm going to talk about growth of functions. We have been talking about it in last week, and in this video, I'm going to solve more questions and gives you, a couple of tips and tricks to solve examples about, comparing the growth ratio of different functions. So last week we talked about asymptotic analysis of the algorithms. When we analyze the algorithms, we need to first find variables that determines the size of the problem. Sometimes just one variable is going to be enough. Most of our discussion have been over the one variable, but even if you have more than one variables, we can just extend our discussions to the cases that we have more than one variable. So just let me show you one example when we have more than one variable. Assume that I have two matrices of dimensions n to m and the other one m to p. I wanted to multiply these two matrices, right? So this simple algorithm shows you how to multiply. Let me change the pen. This algorithm here shows you how to multiply two matrices of different dimensions. And what is going to be the time complexity? The first thing to notice here is that the size of the input is going to be the size of these two matrices, right? One of them is going to be n to m, the other one is going to be m to p. And so we can actually see here that the input size is going to change based on three variables, n, m, and p. All of these three variables directly is going to affect the size of the input, the size of matrices that we are working on. So the time complexity that we recognize for this algorithm will be depending on three variables, not just one variable. So what is going to be the time complexity? You can see that I have three nested loops, right? One of them of size, the number of iteration is n, the other one, the number of iteration is p, the last one, the number of iteration is m. And inside the innermost loop, I just have, a fixed number of simple instructions. So in total, the number of simple instructions that I have is going to be, depending on n multiplied by m multiplied by p, right? And so the whole time complexity will be theta of n to m to p, or you can also say that O of n to m to p. It's just actually showing you one example of the cases where we have more than one variable that determines the size of the input, and so the time complexity of the algorithm will depend on three different variables. One thing that is important to note here is that all these three variables here can grow and go to infinity independently. So that's why we keep all of them in our discussion and showing all of them in the final time complexity, lambda notation for this discussion. So, all those 5 different lambda notation, big O, little o, big theta, big omega, and little omega, all of them had some definition, and we discussed the definition over just one variable. We can extend the definition of all those 3 symbols and extend it to more than one variables, to working on functions with more than one variable. Here I have the definition of big theta for a function with 2 variables, and just like this you can extend it to more than even 2 variables, to 3, 4, any number of variables that you have, and you can just write down the definition for the other symbols very similar to this. So we say that a function f of n and m, 2 different variables, is in big O of g of n and m. Again, this function is going to be a function of 2 these two different variables. And we say that f of n and m is in big O of g of n and m if I can find, this time I need three constants. Again, c and two constants n0 and m0, where for all the values of n greater than n0, so n0 is going to be a threshold for n, m0 is going to be a threshold for m, f of n and m is going to be smaller or equal to c multiplied by g of n and m. So you can see that again, big O is just telling you that g is an upper bound for f when you are defining these functions over two variables. So just similar to this, you can extend the definition of the other lambda symbols. So this is just, a review from this slide is a review from the last lecture. It just, when we discussed about the time complexity of these functions and the growth ratio of them, all these symbols, big O, little o, theta, omega, little omega, all of them is just to tell us about the growth ratio of two functions. So the question is, I'm comparing two functions f and g, and I wanted to know that which one is going to grow faster than the other one. Okay, and these lambda symbols are going to help me to just summarize the point that, okay, if f of n is growing slower than g of n is an upper one, so I write it as, for example, f of n is in big O of g of n, something like this. So when I'm comparing the growth ratio of two functions, one thing that I can do to make it easier for me to understand, or sometimes it's not very clear that which function is going to be growing faster than the other one, it is better to calculate this formula, the limit of f of n over g of n when n approaches to infinity. And based on the result, you can say that which one is going to be growing faster than the other one, or if both of them are going to have the same growth ratio. So the result is going to be either 0, or if it is something less than infinity, it means that it is going to be 0 or some constant number. This is going to fall in this part, the big O. Or if it is going to be, if it is between 0 and infinity, it means that when you are dividing them n approach to infinity, the result is some constant. So it means that the growth ratio of both of f of n and g of them are the same. And if f of n is growing faster than g of n, the result is going to be some constant or infinity. So in this case, it's going to be big omega. Or if it is equal to infinity, it just means that the growth ratio of f of n is strictly faster than the growth ratio of g of n. So that means that g of n is a loose lower bound for f of n. This picture here is just summarizing all those 5 different formulas. You can see that this, for example, if f of n is in little O of g of n, it means that the result here is going to be 0. This is blue, and this one is also blue. That just tells you that, the notations and the result of this formula. Okay, so what we are going to calculate if I'm comparing two functions is going to be calculating this formula, the limit of f of n divided by g of n when n approaches to infinity. We will come back to this, and we are going to use this a lot when comparing two functions. Okay, just before seeing a couple of exercises, another observation or theorems that we can prove is that if f of n is in big theta of g of n, of course, g of n is also in big theta of f of n, and vice versa. So you can see that this relationship is if and only if. So I can prove it simply, basically because, intuitionally, you know that the growth ratio of f of n is equal to g of n, so of course the growth ratio of g of n is also equal to f of n. And mathematically, I can prove these relations. If you had any question about them, we can actually discuss it during the face-to-face sessions, or you can ask me during the office hour. Also, of course, if f of n, if f of n is in big O of g of n, you can show that g of n is in big omega of f of n, and vice versa. So again, here the relationship that we have between them is if and only if. And the same for the little o and little omega. So I think proving them is going to be very simple. The proof is just about showing that if there is a constant for this one, you can also actually find for the other side of the relationship, and vice versa. Okay, a couple of examples here. Which of these statements are correct and which ones are wrong? The first one is saying f of n equal to n is in big O of n square. So n square is, of course, an upper bound for n, so this is going to be correct. N square is an upper bound for n square, and it is big O, so this is going to be correct as well. If it was little o, it's going to be wrong. F of n is equal to this, this formula 3n squared plus 4n plus 5, this polynomial formula, and again the biggest term that you have here is going to be n squared, and here the function is n squared. This is going to be in big O of n squared, because in fact it is in theta, and it is correct to say that it is an upper bound for that. If I wanted to write it more accurately for you, you can write it in this way, that 3n power 2 plus 4n plus 5 divided by n power 2. If you calculate this limitation, you can see that the result is going to be 3. This is going to be some constant, so of course this is going to be in the big O is going to be a correct notation. Also theta is also correct here, just don't be confused about this. So f of n cube is in big O of n square. This one is going to be wrong, of course, because you can see that if I calculate the limit of n cube over n square when n goes to infinity, the result here is going to be infinity, right? Because n power 3 divided by n power 2, the result is going to be n approaches to infinity, the result is going to be infinity. So this one is going to be wrong. How about this one? Again, I know that the limit, this one divided by this one, the limit is going to be constant 1, so we can say that this is correct because this is talking about the big omega. This is a lower bound. Yes, n square is a lower bound of n square. How about this one? So this is going to say that log of n in n square is in big omega of n square. That's just telling you that this is going to be a lower bound for this one. Again, you can calculate the limit of log of n in n power 2 divided by n power 2, n approaches to infinity. You can see that the result is going to be limit of log of n approaches to infinity. The result is going to be infinity, right? And you can say that yes, n square is a lower bound for log n square, so this is going to be correct as well. How about this one? Even without actually calculating the limit, I can say that yes, for n square plus 5, this polynomial term is going to be an upper bound for n square, or n square is a lower bound for this term. Yes, it is, and it is also actually in the same theta, and it is, this one is going to be correct, but the theta of that is going to be correct as well. Here again, theta is going to be correct as well. Again, n cube is in big omega of n square. It means that n square is a lower bound for n cube, and that is correct, obviously. And it is saying that n square is in big omega of n cube, which means that n cube is a lower bound for n square, which is not. Of course, this one is going to grow much faster than n square, so this one is going to be wrong. So only this one and this one was wrong, and the rest of it was very correct. Here you can actually see the summary of the result. And I have another exercise for you. Assume that I have this 7 number of functions, and I wanted to order them based on their Garrett ratio, order them from the slowest to the fastest. So which one is going to be the slowest one, and which one is going to be the fastest one, and completely order them. So if you want to solve a question like this, you might see that some of them are very clear, that, for example, something like this, that I know that this one is going to be faster than this one, for example, or I know that this one is going to be faster than this one, or this one is going to be faster than this one. Some of these are very clear, some of them are not, right? How you are going to compare this one and this one, it's not going to be that clear at the first glance. So before I actually solve this completely and give you the full order, I wanted to give you a couple of tips and small theorems that helps you in finding the growth ratio of comparing the growth ratio of the functions. So the first tip that is very important is that when you are comparing two functions, I have actually mentioned this before, but again, I'm emphasizing on this part. When you are comparing the growth ratio of f of n and g of n, two functions, what you need to do is calculating this limit. Based on the result, you can say that one of these 3 cases would happen, right? So either c is going to be 0, then f of n is going to be, the growth, it's just, if it is 0, it means that the growth ratio of g of n is strictly faster than f of n. Okay, so f will be in little o of g of n, or g will be in little omega of f. Both these two are going to have the same meaning. Just basically tells you that the growth ratio of f is strictly slower than the growth ratio of g. If the result is going to be infinity, it means that the growth ratio of f is strictly faster than the growth ratio of g. And if it is some constant, the growth ratio of both of them is going to be equal. So I have 3 cases, in fact, based on the result of this formula. So what you need to do is calculating the limit of f of n and g of n. Okay. I will actually come back to this one later. One actually very important trick that helps you a lot in comparing, some of these tricky functions is this formula that tells you that if I have 2 functions that which one of them is in the form of n power b and the other one is a power n, okay, for all the values of b, so any value of b, anything basically, and any value of a greater than 1. If a is less than 1, I'm not talking about that case, because anything less than 1, so for example 0.1 power anything, and anything, this one, when n approaches to infinity, this function approaches to 0. Okay, so this function is not a growing at all. So this is going to be out of question. What we discuss in growth ratio of the functions, we are just interested to those functions which are growing. They are, the limit of the functions is going to be infinity. They are growing to infinity. So we are just interested about those functions. So the cases that I'm talking about is going to be the cases where this a power n, a is going to be greater than 1. So with n approaching to infinity, this one is going to approach to infinity as well. You should know that it doesn't matter how big is b and how small is a, as far as a is greater than 1, always the growth ratio of such function is going to be faster than, strictly faster than the growth ratio of such function. So for example, you can see that I wrote some example like this, that n power 100, even a big number like 100, it doesn't matter, even a million, n power a million, this is going to be strictly slower than a function like 1.3 power n. The reason is that the other part, this part, is going to be exponential, and this one is going to be polynomial. We can prove that the growth ratio of this exponential function is going to be strictly faster than the other one. We can always find a constant that actually makes this part strictly larger than the other side. Okay, one trick here that helps you in solving the growth ratio of functions. And the other one, which is very interesting, is this one. That is telling you that log of n to the power of b, again, any value of b, as big as you want, comparing to n power a for any value of a greater than 0. Be careful, when I'm saying any value of a greater than 0, it means that, so for example, n power 1 divided by 7, so you know that this is going to be just a kind of roots of the function, right? If it is n power 1 divided by 2, that's going to be a square root, right? So this one is going to be root 7 of the function of n. Okay, so it is telling you that if you have any function like this that is log of n to the power of b, the growth ratio of log of n to the power of b is strictly smaller than the growth ratio of n to the power of a. It doesn't matter how small is a, as far as this is going to be actually some positive number. Again, be careful, I'm not talking about the negative numbers. If this is a negative, a is negative, then value, this function will be, so for example, 1 over, if a is equal to -1, the function will be 1 over n. The limit of this function is going to be 0 when n approaches to infinity. So we are not talking about the functions which are not growing to infinity. Okay, so n should be some positive number, but it doesn't matter how small is that, as long as it is positive number. Okay, so another example of this is just telling you that log of n to the power of 1000, it is going to be strictly slower than n to the power of 1 over 5. So these two tips, I'm going to actually use them in solving this exercise later. I will come back to this. Okay, what else? Let me see what we had here. Okay, one more very interesting actually theorem that helps a lot in comparing the growth ratio of two functions is this L'Hopital rule. That, as I told you, when you are comparing the growth ratio of two functions, you need to calculate the limit of f of n divided by g of n when n approaches to infinity. But sometimes the functions are too complicated that even calculating this limit is difficult. Okay, so if that's the case, one tip is that we can prove the limit of f of n divided by g of n when approached to infinity is equal to the limit of, the derivative of f of n divided by the derivative of g of n. So if calculating this limit is difficult for you, you can get the derivation of f, get the derivation of g, then calculate the limit for this formula, the derivation of f of n divided by the derivation of g of n. Okay, so for example, I wanted to calculate the limit of log of n divided by n. Of course, I know the result. This one is very simple. I know that this limit is going to be equal to 0, even directly. But even if this is not very clear to you, one thing that you can do is you can get the derivation for log of n. You can get the derivation of n, all of them, the derivation based on n, okay? And then divide the derivations of this and calculate it. So the derivation of log of n is going to be 1 over n. The derivation of n is going to be 1. So the limit of this when n approaches to infinity, this is going to be equal to 1 over n. Of course, when n approaches to infinity, the result here is going to be 0. So n is going to strictly be faster than log of n. Of course, we knew it before. I just wanted to give it as a simple example for this theorem, this L'Hopital theorem. Okay, another very useful actually tip here is if you have two functions, you can actually add the functions, and if f of n, if you know that f of n, for example, is strictly slower than g of n, and another function that f2 is strictly slower, it is slower than g2, or any of these lambda notation relationships that you have between them, you can add them, and the result is going to be, the relationship of the big O notation will be applied over the addition of these functions. Okay, and also over the multiplication of the functions. You cannot actually do it over the division or subtraction, just over the multiplication and addition. One thing that we can actually learn about this one is that, for example, if I know that I have two functions, something like, this formula is going to help me to simplify the functions. So let me actually give you two examples of these functions that I have from before. Let's compare this one and this one. I wanted to know that n power 4 divided by 3 is faster than n log n, or vice versa. When you are comparing these two functions, what you can actually see that you can see this one is going to be n multiplied by n power 1 over 3, and this one is n multiplied by log of n power 3. I can say that this function and this function has the same growth ratio. Okay, so it's just like, and because there is multiplication between them, I can simplify these two sides and say that, okay, forget about this, just compare the growth ratio of these two parts. Which one is going to be faster? The whole function will be actually faster than the other one. And comparing these two based on the previous actually tips that I gave you, you know that n to the power of anything is going to be faster than, strictly faster than log of n to the power of anything. So at the end, I know that n power 4 divided by 3 is going to be strictly faster than n multiplied by log of n power 3. Okay, and one more actually, here it actually just tells you that comparing these two, we can actually solve this using these formulas. Another very interesting function, very interesting tips here is this one that is telling you about the combination of the functions. Okay, so if I have two functions f and g, that I know that the growth ratio of g is strictly faster than the growth ratio of f, and I have a third function h, which is going to be a growing function. A growing function means that h of n, when n approaches to infinity, is going to approach to infinity. If h is not a growing function, okay, just forget about it. We are not talking about those functions. We are just talking about the growing functions. Okay, so if you have such a function, you can combine it and say that if you know the growth ratio of g is strictly greater than the growth ratio of f, the growth ratio of g of h of n is also going to be strictly greater than the growth ratio of f of h of n. Okay? And this relationship will be applied to big O as well. So this is going to be applied to the upper bounds, basically. This one, I'm going to actually use it to solve some of the some of the exercises that I had at that the full exercise that we discussed before. I'm going to solve all of this at the end. Let me see that if there is anything else. Oh, okay, here is just showing you an example of an example of using this theorem to find the growth ratio of two functions. It's just telling you that, for example, I know the square root of n is in little o of n, right? The growth ratio of n is strictly greater than the square root of n. And we know that, for example, log of n is a growing function. The limit of log of n will be infinity when n approaches to infinity. Okay, so I'm going to use log of n as this h function, and when you are actually comparing these two, you can also say that if I have a square root of log of n, I know that this is going to be strictly slower than the log of n. For this case, it is very clear that, of course, the log of n is going to be actually strictly faster than a square root of log of n. But for some examples, you will see that it's not very clear. And using log, mostly when I'm actually using this h, what I'm going to use is going to be either power, so for example, 2 power n as h, or log of n as h. I will actually use these two a lot as h, but any growing function can be used. Here is actually showing you a good example of using this theorem to compare two functions. So I have these two functions. Which of these two functions are going to be growing faster? I believe at first glance it's not very clear that which one is going to be in fact faster than the other one. what on this side you have an exponential function, but the power of it is going to growing very slow. On the other side, you have a multiplication of a polynomial multiplied by some log of n. It's not very clear that which one is going to be faster than the other one. What I can do here is I can apply log of n over both of these two functions. What is going to be the result? If I get the log of 2 of this part, this one and this one, the result of this one is going to be log of 2 power square root log n. So the result of this one is going to be just s square log n, right? This is going to be log base 2. And you can actually take the log base 2 of this function as well. So this is going to be log of n multiplied by log of n power 3. It's going to be log of n plus, I have a multiplication between these two, so it's going to be actually convert to summation. Log of n. And the power 3 is going to actually came out. So this is going to be something like this. Log of n plus 3 log of n. So I have one more. So now I need to compare this function and this function. And now it is easy to compare these two, right? This term here is a very small term, but I have a big term here, so I can actually in total say that if I calculate the limit of log of n plus log of n divided by square root log of n, it is clear this is going to be infinity when n approaches to infinity. This is going to be strictly faster than this one. I can say that his n to the log of n power 3 is strictly faster than 2 to the power of a square root log of n. Although at the beginning it was not very clear to us that which one is going to be faster. Okay, now I think we can actually just go back to solving this exercise. If you get a question like this, the easiest way to approach it is to find some ordering between those ones which are clear. Okay, the first thing that comes to mind when you are actually comparing all these is to know that, okay, among all of these, it's kind of clear this one is going to be the fastest. It is exponential. The power of it is very clear that, again, the power of it is very actually big function, 2 to the 2 power of n. And after that, I think it's very clear that the growth ratio of that one is greater than this one, and the growth ratio of this one is greater than this one. Okay, so far I have this 3, 2 to the power of n. I also have 2 to the power of n power 2. I know this, but I don't know about the rest of it. Then I actually will talk about the rest. And one more thing that I know is that, of course, if I compare this one with this 3, I would know that this one is going to be slower than the rest of them. Okay, so far I know about this 4. This is easy to actually get. But I don't know about this 3 and where they will actually end up. Where in this here, 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 or here. So basically I need to actually find the place of this 3 in actually between all those 4 that I have. Okay, so one thing that I can do here is, first of all, I can do some comparison between these functions themselves. So for example, between these two, we already actually did solve this, right? comparing n power 4 divided by 3 and n to the log of n power 0. So this one you can simplify it as n multiplied by n 1 over 3 and compare it to n to the log of n power 3. So you can actually say that I can simplify it as these two parts will be removed, and it's just the comparison between n to the power of 1 divided by 3 and log of n to the power of 3. Based on that formula, n to the power of a is going to be an upper bound, a loose upper bound, for any log of n to the power of b where a is a positive number. Okay, so of course I know that this function is going to be growing strictly faster than the other one. So far I know that n to the power of 4 divided by 3 is going to be greater than, the growth ratio of that is going to be greater than n to the log of n power 3. Okay, what else I can actually get? I wanted to compare, I need to actually just compare this one as well. One thing that I wanted to do is, for example, comparing, let me use a different color here. Comparing, for example, this one or this one with the last one. By comparing that, I can actually, so for example, if I know that this is going to be greater than this one, faster than this one, the whole these two will be actually end up before here. If I know that this one is smaller than this one, so these two will actually end up here, right? So by just one comparison here, I will do some simplification here. So one thing that I can do is that, okay, I wanted to, let's actually just compare this one and this one. If this one is greater, then the whole thing will be greater than that 2 to the power of a square root log of n. So comparing 2 to the square root log of n and n to the log of n power 3. Actually, we did this comparison just here, right? So we know that this one is going to be strictly faster than 2 to the power of log of n. So based on, again, that comparison, I can here say that, yes, both of these two will be faster than 2 to the power of a square root log of n. And it is clear that they are going to be slower than 2 to the power of n, because that is an exponential function, clearly much faster than n to the power of 4 divided by 3. So the only thing that remains is the position of n to the log of n. I don't know where I should put this one. So let's do one thing. Let me actually just summarize everything that I know so far. So let me actually just make some space and put this to the n to the power of 4 divided by 3 n log n power 3 and 2 to the power of a square root log n. We so far know all this, okay? So at the end, I just actually need to find out the position, the correct position for n to the log of n. To do this, I can, in fact, compare n to the power of log of n to n power, I can actually compare it to 2 power n, okay? Because so far I know that n to the power of log of n, clearly this one is going to be greater, strictly greater than n to the power of 4 divided by 3. This is going to be faster. I think that's just clear. I don't need to really prove this because, you know, compare these two functions, n to the power of 4 divided by 3 and n to the log of n. Okay, compare these two. If you take the, let's use that log combination. If I take the log out of this and I take the log out of this, the result of this, on the top will be 4 divided by 3 log of n. The result of this one on the below is going to be log of n multiplied by log of n. Which one is going to be greater? Of course, this one is going to be greater because it has 2 log of n powers and the other one just has a 4 divided by 3 and 1 term of log of n. So it is clear that n to the log of n is going to be greater than this one. I just don't know if it is smaller than to the power of n or greater than to the power of n. So I need to compare these two functions. Again, to compare these two, I can take the log out of both sides. If I take the log of this side, this is going to be log of n multiplied by log of n. If I take the log from here, the result is going to be n. Okay, log of n multiplied by log of n is greater or n? Of course, n is strictly greater than log of n multiplied by log of n. Again, you can actually just, I think it's very clear, but that formula, remember that log of n to the power of anything is strictly slower than n to the power of any positive number. So it's very clear then that here n to the log of n is strictly slower than 2 to the power of n. And so the final full order of all those functions is going to be this order. So this is the result of this exercise. I have one more exercise for you that I'm not going to solve it here. You can actually try to solve it. Some of these functions are going to be, in the previous example that I showed you, there is no, none of these two functions are in the same growth ratio class. So there is no theta relation between any of these. But for in this exercise, in the last one, this is an exercise from your actual textbook, CLRS. Some of them are going to be in the same class. So let me actually show you that. For example, this one and this one, they are going to be in the same growth ratio. Okay, so it is possible that some of these functions are going to be in the same growth ratio class. But at the end, I wanted you to order, find a full order between all of these functions. And if they are in the same class, you can just put them in the same class. Otherwise, you should find the complete growth ratio order of these functions. I will post the result on Blackboard, or we can actually discuss it in our class. Okay, I'm going to actually finish this lecture. You can actually do more exercises in chapter 3. Many very interesting actual exercises and examples you can find in chapter 3.